Hello, everybody. We are back for your favorite weekly series, Watch Your Professor Grade. So, we got six more this time, and let's jump right in. So, let's see. In this one, we have a function f from a domain D to the real numbers. Alpha is some real number, and a is a limit point of D. Prove that if the limit as x goes to a of f of x equals L, then the limit as x goes to a of alpha times f of x is equal to alpha L, and oh, right off the bat, okay, we got to remember our periods in there. All right, let's see. Since the limit as x goes to a of f of x is equal to L, so here we have a comma, and then we're starting with a math symbol. Okay, so this is one of our issues. Okay, so this is number 13 right here. So the goal is not to do this because it actually can make it very hard to read and parse. Are you saying that since this bit is true, then this is true? Are you saying that um, uh, this is true and this is true, right? Because a comma usually could be a list, like this and this and this and this, and so forth. So we want to put some words in there. I expect in here, well, it's actually not really even clear to me what it is. So since this limit is L, A dot is a D sequence that converges to A. So I think what the author is trying to do here is to, and it's confirmed by what's coming next, is to start doing a sequential characterization. So uh, I think just right from the beginning, we want to say let A dot be a D not equal to A sequence. Now, that converges to A. Now, a couple things first here, right? That here, that there, that's got to be in math mode. Now, this is a D not equal to A sequence, so there's a hyphen in between these. So probably a good way to start this would be get rid of this bit here. Let A dot be a D sequence that converges to little a. Okay? Then we don't even have to worry about this issue 13 coming up. Okay, so we just let A dot be a D not equal to a sequence that converges to A. By the sequential characterization of functional limits, the limit as x goes to A of f of A dot equals L. Okay, so again, that needs to go into math mode. Okay, fine. So we do know that. Um, except now this limit doesn't make sense as we've written it, right? So there's no x anymore. There's just this a dot. So we would just not have this down here, right? So when we were talking about limits of, say, a function applied to a sequence or just limit of a sequence, we didn't have to put anything underneath. We said we could write like some n goes to infinity, but only if we were writing a sub n. Okay, so we can write it like this. By the algebraic functional limits theorem, good. Okay, so I like this. So we're just going to break it back down into the theorems that we have already proven. So, okay, so again, we don't want this there. The limit of alpha times f of a dot is equal to, right? Okay, alpha times it, right? We can pull alpha out because this is a regular limit of sequences. Okay, except this is now functional limits as opposed to just sequential limits. Okay, so this is probably the wrong one. Okay, so for sequential limits, we know we can pull out alpha, right? We have homogeneity property. And now, of course, we're utilizing, right, again, the sequential characterization of functional limits if we know that the limit of this sequence is equal to alpha L, right? So this is always true, right? No matter what the sequence was, and it must be because we chose a dot arbitrarily, then it is true that the limit of, well, now it's a functional limit, right? Same thing here. We don't have that, but now when we do have a functional limit, the limit will be the same thing. So probably it would be good to say here again, applying again the sequential blah 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 characterization dot dot dot. We obtain right? You can get rid of the thus there. Because the thing is we're using the sequential characterization in two different ways, right? In the first way, we're saying, oh, well, we know this functional limit exists, therefore the sequential limit exists. But now at the end, we say, well, now, given that all of the sequential limits exist, we know that the functional limits exist. So we're actually using this theorem twice. Okay, so yeah, this should be not too bad to correct. All right, let's go on to our second proof. And oh boy, that's taken a lot of space. I see that right off the bat. Okay, so well, we have some grammatical issues in terms of the punctuation, right? So this comma, that needs to be there, and this period, that needs to be there. So you need to put those inside, right, the equation. Now, I think I get what the author's trying to do here, breaking these things up and putting them on their own line so it's really easy to see everything. This is probably a little too much, right? This problem shouldn't take that long. Probably this right here, that can go up, the and this, that can just go up. And maybe if you want to put like the conclusion on there, right? That might not be too bad. Honestly, it all can just fit on a couple of lines, but okay. Your taste may vary. Okay, so now the limit of, I don't know why we have outside parentheses here, the limit of f of x plus g of x by algebraic function of limits equals the limit of f of x plus the limit of g of x, which equals k plus l. Yeah, so the problem is you're using the theorem that we are trying to prove. Like this, that is why you're doing this on the homework, right? The homework is about proving this result that we wrote down in class and said you have to prove on the homework. So all you're doing is stating that it's true because of the theorem, but this is what you're supposed to be proving. Okay, so yeah, that you're going to need to go back to the drawing board here and actually prove this from scratch. All right, let's go to our third proof. All right, so now we have a function with domain D. We have a limit point for D. And we're going to define the absolute value of the function simply by, well, when you apply it at some point, you just take the absolute value of whatever you got when you applied f at that point. And we want to prove that if the limit, the a limit of f of x is equal to L, then the a limit of the absolute value of f of x is equal to the absolute value of L. All right. All right. Well, okay, so what you're doing here is you are saying since what you're trying to prove, okay, as if this was true, but we're trying to prove that, okay? So we do not assume that which we are trying to prove. Okay, now it looks like at the end, right, you're going to conclude this anyway. And we can immediately see there's a missing period there. So probably this just needs to be eliminated. Okay, so we can start a sentence, capital letter, let epsilon be greater than 0. Fine. So we're using the E, right, the backwards E for there exists. And if we jump down, you can see, yep, this was number 20 on the list. Please don't do that anymore. Okay, fine. So you just write this in words. There exists this delta. Of course, this should be a positive number, such that if x is in D, and if x and a are not equal to each other but are within delta of epsilon, then the difference between f of x and L is less than epsilon. Okay, so what you might have wanted to do is maybe you were trying to quote this piece, right, rather than the conclusion. In which case, you'd want to do that after you've already chosen the epsilon. So you would say, let epsilon be greater than 0. Okay, and now let me put a little star in here, and you'd add in, since the limit as x goes to a of f of x, no absolute value equals L, well, we just say there exists delta of epsilon greater than 0 dot dot dot. Okay, and now everything is going to be fine. Okay, proven from problem 15 in homework 1. Okay, so this is not really a complete sentence. There's a name for this. It's called the reverse triangle inequality. So, and right now what you're doing is just writing down the general statement. This is unnecessary. So we can actually just say by the reverse triangle inequality, by the reverse triangle inequality. Now we can go down here. We have, okay, the absolute value of f of x minus the absolute value of L is less than or equal to, okay, so this is where the reverse triangle inequality is here. Now this is less than epsilon. Okay, one little comment about this, we'll put a little double star. You can see when you start using multiple absolute values in a row that this can get very difficult to read. So what you might want to do in the code is write a slash big before the first absolute value sign. Then you can do another absolute value sign, f of x, absolute value minus absolute value of L, and then another slash big before the second absolute value sign. And what you'll see is that like this is going to make a small but important difference. So I've coded it up for you, so let's take a little peek quickly. What happens when I use this code, right? You can see it's made these absolute values slightly bigger, which makes it a lot easier to read that, okay, oh, I'm taking the absolute value, of this difference, and it's this absolute value of f of x minus the absolute value of L that are on the inside, right? It just makes it a little bit easier, right? Somehow you up here it almost looks like you have an extra absolute value around this f of x, okay? Whereas the size can really help you. Sometimes you might need some bigger ones, so you can use big to maybe get something like normal would be like here, and then big might be here, and then you can also go with a capital B, and that'll make it even a little bigger. You could go back to a lowercase but add another G, and that'll even make it a little bigger, right? So you have different sizes you can play with, and I think you can probably do a capital B here, and then of course that should just be absurdly big, right? So, yep, so when you're having these embedded absolute values or even parentheses or brackets, this will all work with that. Okay. And then at the end here, yeah, this implies that this is equal to that is equal to that. That's fine. Okay. So let's move on to the fourth one. So let's see. F's function from D to R, A is in D. Prove that if F is continuous at A, then the absolute value of F is continuous at A. So keeping this thread of a function versus its absolute value function. Since the epsilon, or let epsilon rather be greater than 0, since F is continuous at A, there exists, okay, you don't need the article a, you can just say there exists delta of epsilon equal to, actually, in this case, we would typically write the delta first, but I tell you what, in this case, just get rid of it, okay? And the reason why is, the reason you would want to write just delta down is to save yourself a little bit of space. But you're only using delta a single time in the rest of this proof, right? That's the only time you're using it. So you know what? Just call it delta of epsilon and just, put that in here. No need to save yourself like that space by losing more space up above. So there exists delta of epsilon greater than 0 such that if x is in D and x and A are within delta of epsilon, then the difference between f of x and f of A is less than epsilon. Okay. By the reverse triangle inequality, it follows that, so same thing as I was saying before, right? Maybe use a big in front of this. That'll make it look a little bit nicer. It follows that the difference of the absolute value of f of x minus the absolute value of f of A is bounded by the difference between f of x and f of A, which is now less than epsilon. Thus, the absolute value of f is also continuous on A. Yep, okay, there's not much to say. I think this is a pretty clean proof here. Yeah, there's not too much more that you need to do. All right, let's look at number 5. Okay, so now we have f going from d to the real numbers, and alpha is a real number, a is a limit point. Prove that if limit as x approaches a of f of x equal to L, then the limit x approaches a of alpha times f of x equals alpha L. Okay, so you're going to start by supposing that alpha is equal to 0. Okay, fine, we can do that. We have that the limit 0 times f of x as x goes to a is equal, oh, it looks like there's a little space missing right there between the limit and 0. Okay, yeah, certainly as x goes to a, the limit of 0 is 0. I buy that. Okay, so yeah, and maybe it's good to put down 0, which is equal to 0 times L, because now we have, right, that we've pulled the 0 out and matches what we've had up above. Okay, now suppose alpha does not equal 0. Fine, let epsilon be positive. There exists a delta of epsilon greater than 0 such that it's not that such that this happens, right? It's such that if this happens, then this happens. So the way you could phrase this, not with an if then, but you could do is get rid of this comma and the which. So such that x and d and x and a between 0 and delta of epsilon implies f of x minus L is less than epsilon. Okay, so that we could do. Fine. Choose some, so you're saying in this second line that there exists a delta. Okay, so it's there. That's it. It's been chosen, right? There's this delta. And now you're saying choose some delta. Okay, so we can't have both of these. These are incompatible. And you're saying such that f of x minus L is less than epsilon over the absolute value of a. And then you want to use the inspired choice theorem, which it seems to me that if you're going to use the inspired choice theorem, you don't have to play this game right here, right? I think you can just get rid of this. And you could say by the inspired choice theorem, we have, let's see, absolute value of alpha x minus alpha L is equal to, okay, and that we want because, right, we're trying to figure out this difference. It's equal to the absolute value of alpha times the difference between f of x and L, which we already know is that last bit is less than epsilon. So this will be, yeah, that's what we could do here is actually, if you want to use the inspired choice theorem, then just get rid of this, and you just say, okay, this is less than alpha times epsilon, get rid of this epsilon. And so actually what you're going to move this down then. You say, we have, this is true, so this is less than alpha and epsilon, and then by the inspired choice theorem, get rid of the hence, we have that this limit is equal to alpha L. Okay, so the inspired choice theorem, if you haven't seen this yet, right, this is saying, right, normally when we want to show that a limit exists, we know that we need to get the difference of the outputs to be less than epsilon. But the inspired choice theorem says, actually, no, you just need to find some k positive such that if epsilon is greater than 0, then there exists some delta of epsilon greater than 0 such that x in d and x and a within delta of epsilon of each other implies that the difference between f of x and f of a, which in this case is actually going to be L, or, well, the limit is going to be L, is less than k epsilon. Okay, so the inspired choice theorem says if the limit as x goes to a of f of x equals L, then, okay, and then this stuff, right? And it's if and only if. Okay, and the important part is actually the one going up. So if you know that you can get the difference between f of x and L, not to necessarily be less than epsilon, but just some constant, some positive constant times epsilon, then the limit actually exists anyway. So that's what we could do here. And of course, this is positive because of your assumption that alpha is not equal to 0. Right? In the case where alpha is equal to 0, then yeah, you just get this immediately. Yeah, it looks really bad, right? If you let alpha equal 0, then all of a sudden it's supposed to be less than 0, which can't happen. So this is why we need to have this special case. Okay, let's go to our final one, number 6. Looks like same question here. So, so the first words that I'm seeing here, the limit as x approaches a, f of x equals L. So when we use the symbol lim, and it's very strange here. I think there's maybe some space missing. I see this all over the place. When you're using this symbol, already that includes the word the. All right, this is the a limit of f of x, and so you don't want to have the word the here. Now you're not going to be able to start the proof just with the limit, right? That's essentially the 13, right? It's void starting sentences or new clauses within a sentence with symbols. Okay, that's this guy over here. So we could say something like, as this limit is equal to L, get rid of the implies that. For every epsilon greater than 0, there exists delta of epsilon greater than 0, such that f of, okay, and actually you could use a little big in front of the parenthesis here and in front of the parenthesis there to make this a little easier to parse. F of this interval is going to be contained in the L coin of radius epsilon. Okay, so that would be fine. Now you say if f of x, okay, and I don't know what x is. And that's important. You're saying if f of x is contained in here. So yeah, so we needed to say what x is. So what is x? Are you talking about an x coming from this a coin? In which case there is no if. I'm not really sure. So you say then by the reserve. Okay, that's a spelling mistake. It's the reverse. Triangle inequality. You don't have to say theorem on that. You can just say reverse triangle inequality. We have this guy. Okay, so it kind of sounds like you're just repeating what you were saying up above. All right. So if if this second one is what you want, which based on what you're doing down below looks like it, then I would just go right to that. So there exists delta such that, let's see, if such that, just get rid of this. Okay, so what is this x? Well, it looks like you want it to be in this a coin. Of course, it also has to be in D because that's the domain of the function. So what is x? The answer is x is in D, and x and a are within delta of epsilon of each other. Okay, so you're not going to want to say this bit. You'll want to actually say this bit. Okay, so what do we have there? As this is true, there exists such that if x is in D, okay, so then we can stop the sentence and we say, oh, we're not quite done yet, right? Oh, yeah, right. We need to do this second half. This reverse triangle inequality, I think, is coming way down below, right? That's not what you're using to get here. Okay, so this reverse triangle inequality that's going to be used down here. Okay, so if this is true, then you don't have to have the we have now, then this is less than epsilon. Fine. Okay, now you're doing all this stuff with epsilon, and then out of nowhere you decide to do the alpha equals 0 proof, right? And then you're going to jump back to the alpha not equal to 0. So let's do this logically, right? Bring this to the front, right? Move to the top. Okay, you can do that first before you do anything. Now, one thing I will say right here, there's a then. Okay, so let's go to our little list. This is number 8. Okay, we use then with ifs. We're not starting our sentences with then. Okay, so now you can jump back into the alpha not equal to 0 case. Okay, suppose this. Okay, we have, and this is where actually we can now take this reverse triangle inequality, and we can say by the reverse triangle inequality we have, okay, this limit is that, no, that's not true. This limit does not equal this absolute value. Okay, so that's gone. It's just false. The difference between alpha times f of x and alpha L, and I don't think we need this extra parenthesis here. This difference is less than alpha. How do we know that? We're trying to prove that. Then you wrote epsilon equals the absolute value. No, oh no, okay. I think you might be saying that you think this expression is equivalent to that expression. That's what I'm guessing you're saying. This is not a real construction. Like, this is not correct math grammar. So if we were writing this on paper, right, you might say, oh, I have this expression. Let me call this A, and this expression, let me call it B. And you might say A is equivalent to B. But this does not mean the same thing as A equals B. Right? A equals B says these are equal quantities, right? As opposed to these are logically equivalent mathematical statements. Now, you're not allowed to use this either in the proof. In fact, that's down here, number 20, we talk about these sort of things. So I'm actually going to add this as issue 24 to our list, because this is not the first time that I've seen this occur. So do not use equal to indicate that two statements are equivalent. Okay, so we got issue 24 there. So what you really want to do is actually just compact this thing all together. So we have alpha times f of x minus alpha times L. And you're claiming, right, that actually you can pull this alpha out, which you can, because we have a property for the absolute value that says you can do that. And now you know by what you have up above on this line, we know that this piece is less than epsilon. And so this product is less than the absolute value of alpha times epsilon. Now, somehow when you did this, your absolute value of alpha got to the bottom, which doesn't make any sense. Okay, now I'm not sure what this is, but I think what you want it to be is the positive real numbers. Okay, so once we have this, right, now notice, like, I have this is equal to that is less than that, and therefore, right, so if this was A, B, C, I have A equals B less than C, and that implies that A is less than C. So I can just anticipate my reader being able to put that all together, that A is less than C. Okay, and now you don't need any of this. Well, maybe you could say since A is a positive real number, the Inch theorem, right? Inch, by the way, is another shorthand for inspired choice. The Inch theorem, okay, again, we want to have words in between. We can say implies that. Okay, and there we go. So, yep, I think all of the ingredients are basically in this proof, right? But we just need to, rearrange a lot of them and, work on the mixture. All right, everybody, we will see you next week with more Watch Your Professor Grade homework.